Hello to all the EMBC community. I hope you are enjoying the virtual version of the conference, and let's pray that will be the last virtual meeting. My name is Konstantinos Montouris, and during this talk, I will share with you the work we have been doing on mesh-free methods and the application of cardiac electrophysiology simulation. Most of you should be aware that simulation is a fundamental part of research in cardiac electrophysiology. Computational models that span from cellular up to the organ level are under continuous development and provide significant insight in the mechanisms of the cardiac function. But the question is why the clinical application of simulation remains limited, while in research simulation is thriving. Our goal is here to identify this reason and propose an alternative to overcome this limitation. To do so, we will provide a brief review of the state-of-the-art solvers in cardiac electrophysiology, and then we will introduce the mixed collocation method, an alternative mesh-free method that we use to derive the monodomain model for cardiac electrophysiology simulations. Based on this new method, we will propose an image-based modeling approach with a great potential for clinical applications. Finally, we will validate this new method and we will provide some discussion and conclusions. To start, the state-of-the-art solvers are usually employing the monodomain model to simulate the cardiac function at a multi-scale level. This model is described by the reaction diffusion equation, where the reaction term is used to simulate the action potential generation at the cellular level. The diffusion term is used to simulate the propagation of the electrical signal in the tissue considering the boundary conditions of insulated borders. Using the finite element method, the solution of the monodomain model is achieved. The main advantage of FEM is that it is a robust and accurate technique that is well established and extensively used in research and industry. However, the accuracy of FEM may suffer from mesh distortion and is necessary to generate a mesh of good quality to ensure high accuracy. Moreover, meshing is a time-consuming task that requires significant engineering skills that are not available in the operation theater, and this is the main reason why electrophysiology models are not widely used in the clinic. But what if we could avoid meshing? Would be a mesh-free method suitable for the requirements of the clinical setting? Well, this is what we want to prove by introducing the mixed collocation method, or in short MCM. MCM is a mesh-free method that employs interpolation to approximate both the field variables and its gradient. Being a purely mesh-free method, it does not require any connectivity information. Now looking at the figure, the interpolation for a field node, denoted by capital I, is performed inside a support domain which is composed by the neighbor nodes to the field node of interest. In our work, we are using the moving Kriging interpolation to interpolate the field variable and the gradient. We chose this interpolation scheme because it possesses the delta Kronecker property that allows the directly position of essential boundary conditions. Now, writing the diffusion term in its Petrov-Galerkin weak form and applying the moving Kriging interpolation to both the field variable and the gradient, we can finally obtain the MCM mesh-free form of the monodomain model. The main advantage of the MCM is its high flexibility to discretize the geometry. This allows to introduce the notion of immersed grid discretization for the automatic generation of the model. It's very easy to generate the model by simply extracting the surface of the geometry from the image data and then creating a grid of nodes that are distributed regularly inside the bounding box of the surface. Using an inclusion algorithm, we can discard the nodes that lay outside of the surface and obtain in this way the final mesh-free grid. This approach allows us to introduce the pipeline for automatic image-based model generation. With this method, medical image data can be converted directly to a model and obtain results from simulations that can be interpreted in the 3D or the image coordinate space. The proposed pipeline starts with an initial image processing step. In this work, we consider a diffusion-weighted MRI image of a porcine biventricular anatomy that we initially segment into three regions that correspond to the endocardium, mid-myocardium, and epicardium of the ventricles, considering a 45 to 25 to 30 ratio. Furthermore, we compute the diffusion tensor at each voxel of the image applying a Riemannian distance minimization algorithm to the DWI data in order to obtain the fiber orientation. Next, from the segmented image data, we generate the mesh-free immersed grid. To do so, we use the Delaunay triangulation to extract a triangular surface mesh of the biventricular anatomy. Now, instead of distributing nodes inside the bounding box of the surface, we convert the actual voxels to mesh-free nodes, considering only those that lay inside the surface. Next, we introduce the conduction system in order to apply the electric stimulation to the model. We construct manually the bundle of His, and we generate the Purkinje branches automatically using a fractal tree algorithm, and by this we have the complete model. Following, we perform the simulation of the electrical signal propagation from the conduction system to the biventricular anatomy, and we generate color maps for both the local activation time and the action potential duration at 90%, aka APD90. For the simulation of the electrical signal propagation, we use Electra, which is an in-house cardiac electrophysiology solver, and we compare it with FEM. Given the number of nodes in the MCM and the FEM geometries, we observe that MCM does not introduce any significant overhead in terms of execution time. Furthermore, comparing the local activation time color maps of MCM and FEM, we see that MCM results are in good agreement with FEM, and we obtain a high normalized histogram intersection index, which from now on we will call it NHI index. Similar results are obtained from the action potential duration at 90% of repolarization. The NHI index is a bit lower compared to the local activation time color map. The difference is due to the increased number of nodes that are repolarizing in the range of 220 to 250 milliseconds for the FEM simulation. Nevertheless, the APD90 is in the same range for both methods, and the mean values are in close proximity, demonstrating that MCM can produce results with comparable accuracy to FEM. In the previous example, we demonstrated the feasibility of automatically generating an image-based mesh-free model. Indeed, starting from the image data and its segmentation, we obtained an image-based mesh-free grid. We used the MCM method to simulate the electrical signal propagation and generate color maps from the local activation time and the APD90. Most importantly, the fact that each node of the mesh-free grid corresponds to a voxel of the initial image allows us to interpret directly the results of the simulation in the image coordinate space. Therefore, we can conclude that MCM can completely alleviate the requirement of a mesh. This allows to generate a mesh-free model directly from the image data in an automatic way with minimum input from the user. Moreover, the results have comparable accuracy with FEM and they are obtained with similar time efficiency. So finally, MCM has a great potential for the integration of simulation in the clinical setting due to its capacity for automatic model generation and direct interpretation of the simulation results on the image coordinate space. At this point, I would like to thank you for your attention, and I hope that you found interesting this presentation. If you would like to get in contact with us, please follow the QR code at the bottom left corner. And if you are interested in the references that we are citing in this presentation, please follow the QR code at the bottom right corner. Thank you.